Now that we've covered amino acids, probably more than you, did you ever cover amino acids like this before in any other class? No. Okay. Well, let's start putting them together. Covalent bonds join our amino acids, and they're called peptide bonds, also known as, what are they also known as? The peptide bond is also known as one of our functions, an amide bond, that's right. It's known as an amide bond. So what happens is we condense, remove a water molecule, the amine of one amino acid, and the acid of another one. We're going to remove 2 hydrogens from the amine and then 1 oxygen from the acid and form a covalent bond called the peptide bond. And I think this works. I think there might be a commercial, though. Oh, no, there's no commercial in this one. Look at that. How cool is that? This is what I do with my free time.
Do it again.
Do it again. Come on. Go. So see the water molecule moving, going away? The hydrogen. It depends on the charge, what's going on. So hydrogen here, the OH here, you remove a water molecule. Come on. And then you form a bond here. Pretty cool. I'm not going to ask you to draw the reaction, but I want you to see that it's a condensation reaction. I do want you to know that the peptide bond is formed between the amine of one amino acid and the acid group of the other amino acid. And that water is removed from this reaction. So here we can do it. That's why peptides and proteins are called polymers, because we're putting together a bunch of them in the same reaction. And so we get our peptide bond. So, and water is lost from it. And notice that we have the different R groups hanging off. So here we call this our backbone. You have an N terminus and a C terminus. N terminus is where you have your nitrogen, your amine group free, and the C terminus is where you have the acid free. So you have your N terminus, alpha carbon, carbonyl, nitrogen. So this is your peptide bond. Alpha carbon, carbonyl, nitrogen. That's your peptide bond. Alpha carbon, and then here's your C terminus. So here it is a nucleophilic attack. It's a condensation. Lone pairs on the nitrogen are going to attack our partially positive carbon of our carbonyl. Now, if you look at it, this nitrogen should have a lone pair on it. So it should be sp3 hybridized, which is it's from the 4 electron groups around the nitrogen. And so it should have a tetrahedral shape. However, when they do experiments to look at the geometry, this is not sp3 hybridized. It is actually sp2 hybridized, meaning that is trigonoplanar. We would expect this carbon to be trigonoplanar because it only has 3 electron groups. But this one is perplexing. Why would this be actually sp2 hybridized or trigonoplanar? What's going on there? The lone pair is doing what? It's moving around. It's moving around because you have resonance structures. And let's take a look at that. So here I'm talking about this nitrogen. This is what we're thinking. This nitrogen should have this, okay? It should have the one bond with the carbon of the carbonyl. This is our peptide bond right here. The hydrogen, the alpha carbon right here, and the lone pair. This is what it should have. So it should have the 4 groups, which makes a tetrahedral shape. But it doesn't. What happens is that these lone pairs are actually in resonance with the lone pairs, the double bond. Whenever you can have the double bond travel around, okay? The double bond can travel around through resonance structures. The reality is not that it does travel, okay? We don't have a flipping back and forth. What we have is double bond character throughout this entire thing. And when you have resonance structures, when you have the ability for those pi electrons to travel around or spread out between more than one bond, then it makes a very, very stable structure. So this peptide bond is planar, is rigid, because double bonds don't have free rotation. That's right. They don't have free rotation. So that peptide bond does not. That has huge implications on the structure of our proteins. Huge implications. There's only free rotation around our alpha carbon. There's not free. This is rigid. So the single bonds, they can rotate. Double bonds, you can't. So it's a very stable structure. So because this, okay, we're going to show the double bond character here as these red dots. So what happens is when you have your chain, your polymer of amino acids, you have the peptide bond, which is rigid. There's free rotation around the alpha carbon, so we have that tetrahedral shape. And then your R group hangs out. But what happens is the peptide backbone actually is a zigzag shape, and we'll show that next slide. But in that zigzag shape, your R groups go above and below. So let's say we take a protein and we string it out. And I pull on both ends and just make it straight. What's going to happen is that in successive amino acids, R group down, R group up, R group down, R group up. And so they go back and forth. That has huge implications when we start folding our proteins. So here, the red are nitrogen, the blue are oxygen, and the black are carbons. Here we're showing the N-terminus here and the C-terminus here of our peptide. And you can see the backbone, okay? Remember the backbone. Nitrogen, alpha carbon, carbonyl. Nitrogen, alpha carbon, carbonyl. Again, so that's what I'm talking about, the backbone. You guys need to know what I'm speaking about when I say the amino acid backbone. That means that the R groups are hanging, dangling, ready to interact. So we can see the glycine is above it. Here's a phenylalanine. Here's another glycine. Here's an alanine. Here's a leucine, a serine, a glycine, another alanine. What's that guy? A glutamine. No, glutamic acid. Sorry. And the C-terminus. So here you can see that it's up, down, up, down, up, down, opposite sides. When we get to beta sheets, that's going to be very important. So here we're showing a small chain, which is our peptide. It's a shorter chain. If it's just 2 amino acids, we call it a dipeptide. Surprisingly, if it's 3, we call it a tripeptide. But then once we start getting more in there, we call it a polypeptide. Then we definitely change the definition to a protein. Again, here's a different definition. And I throw that in there so that you guys are familiar with it. Sometimes it's 5,000 Daltons or grams per mole for the cutoff. Again, we're going to say 50 amino acids in this class. But some of these dipeptides, tripeptides, are, when you have just a small one, are biologically active. So just like we saw, single amino acids are biologically active. Here we have some dipeptides that are biologically active. Here's beta-alanine. So here's, it just has 2. It doesn't have just an alpha. It's a beta amino acid. And does anybody know what carnosine does? No, it's an antioxidant. Here's a polypeptide. Has a dicyl bond. What is the difference between oxytocin and vasopressin? There's only one difference. There's, I think, let me see. There's 2 differences. In position 3, isoleucine and phenylalanine. And Position 8. So there's 2 amino acids. And what does oxytocin do? Yes, that's right. And vasopressin is very different. It increases blood pressure, right? And reabsorption of molecules into the kidneys. So look, very different.